Today on the Perception in Action podcast, how do implicit and explicit learning interact with each other? If a coach gives an athlete an explicit strategy for correcting their technique, is it going to hinder implicit learning? What does this have to say about whether it's a good idea for a coach to sample from and mix different theoretical approaches? So it's time for a call to action. Hello, and thanks for joining me. This is Rob Gray from Arizona State University. I've been on a now over 25-year journey as a researcher, professor, and high-performance consultant to understand how we acquire and adapt our perceptual motor skills. Welcome to the Perception in Action podcast, where I discuss how psychological research can be applied to improving performance, accelerating skill acquisition, and designing technologies. If you're a coach or an instructor, my goal is to help you bridge the gap between research and application, and to connect your experiential knowledge with skill acquisition and motor learning theory. I want to help take you from using practice design recipes to becoming a master chef who can manipulate the key ingredients to come up with your own innovative training methods. If you're a student or fellow academic working in the skill acquisition field, I hope to keep you up to date on the latest studies and help you get to know the people working in this area. Finally, if you're developing training technologies, I hope to help you incorporate good motor learning principles in your design, pull out key performance metrics from the data, and design effective studies to evaluate your product. To learn more, help support the podcast, and/or work directly with me, please check out perceptionaction.com. Now on to the show. As I first discussed back in episode 190 when talking about prescriptive instruction versus self-organization approaches to skill acquisition, I have a somewhat controversial opinion with regards to coaches mixing different methodologies in practice. While I think it's great to mix different types of methods like changing conditions, adding variability, altering feedback, etc., I don't believe it's a good idea for a coach to pick and choose from different theoretical approaches. For example, using a repetitive drill design to get the athlete to learn the quote-unquote fundamentals of an ideal technique in one session, then switching to an activity designed to encourage exploration and self-organization in the next. As I discussed in that episode and a few recent blog posts, to me, having an inconsistent theoretical approach in coaching philosophy leads to weak and counterproductive interventions. In today's episode, I want to look at another example of a body of research that I think gives some support to my view. Specifically, I want to look at work that has investigated the interaction between explicit strategies for correcting errors in technique and implicit learning. Is it a good idea for a coach to encourage an athlete to use both of these together? For example, should a golf instructor use a practice activity designed to promote implicit learning, like errorless learning, while also giving a cue like, when you leave putt short, you need to lengthen your backstroke? Is mixing these two different ways of learning a skill effective? To address this issue, I want to look at a set of studies that have used the well-studied visuomotor adaptation paradigm. I talked about this a few times on the podcast now, but as a reminder, in this task, participants are asked to move a cursor on a screen towards a target. The cursor is controlled by the movement of the person's hand via a joystick or a motion tracker. To investigate adaptation and learning, a rotation is added to the mapping between the movement of the joystick and the movement of the cursor. So for example, if the person moved the joystick straight up, the cursor might go 45 degrees to the right instead. Previous research has shown that participants can learn to compensate for this rotation and hit the target in two different ways. The explicit component of learning can be assessed by asking participants to indicate their aim point before they start moving. So for example, if you asked me to move the cursor to the top of the screen, and I told you that I plan to aim 45 degrees to the right, it would indicate that I'd figured out the manipulation and am adopting an explicit strategy to counteract it. But this research has shown that participants also learn to adapt implicitly, that is, without awareness of any explicit strategy. This can be seen by the fact that even though participants indicate an aiming point, they usually do not actually move there. The difference between the aiming point and where they actually move has been used as a measure of implicit learning. The type of learning going on can also be assessed by looking at after effects. If participants are using only explicit learning for the task, if you take the rotation away and tell them about it, there's no after effect. They will hit the target because they can just consciously stop using their aiming strategy. For implicit learning, however, there's a large after effect seen as an error in the opposite direction to the original rotation. To alter implicit learning, the participant is going to have to recalibrate by doing some practice trials without the rotation present. Another way to think of this is playing golf on a windy day. If there was a really strong crosswind from left to right, there would likely be two processes going on to allow you to keep hitting the ball straight. An explicit strategy of, I'm going to start the ball out a bit to the left so the wind carries it back to the middle, and an implicit process, whereby the calibration between the information and movement is changed to alter the path of your swing and the flight path of the ball. For example, making the ball work from right to left into the wind. Do these two processes complement each other? How do they interact? The first study to address this question using the rotation paradigm was by Bazzoni and Krakauer in 2006. In their paper, they noted that most people assume that the explicit strategy can act as a substitute for slower implicit learning. To test this, instead of waiting for participants to learn the explicit strategy of aiming to the left, they gave them a cheat code. They actually told them that there was a rotation present and that they could easily counteract it by, instead of aiming at their goal target, aim one target to the left. 18 participants moved their hand to move a cursor towards one of the targets lit on the screen. Targets were arranged in a circle and separated by 45 degrees. There were three basic phases: a baseline with no rotation, a series of trials with the 45-degree rotation in which participants were given the cheat code strategy, and then a set of trials with the rotation taken away to measure after effects. Finally, results were compared to a separate set of data from when participants learned the task without the cheat code. The error between the target and the cursor location was the main dependent measure. What was found? For the phase in which the rotation was present, giving the participants the explicit strategy of aiming one target to the left was initially very effective, as errors almost immediately dropped to zero. However, then something very interesting happened. Even though nothing about the actual task changed, participants started making movement errors. When interviewed after the study, participants actually expressed frustration with the fact that despite their strategy, they were getting progressively worse at the task. It was like their hand was possessed. What's going on here? Well, with practice, participants were learning to implicitly recalibrate their hand movement in response to the rotation. When this recalibration is combined with the explicit strategy, it actually makes them fail at hitting their target. Using my golf example again, with continued practice driving in a crosswind, we may learn to implicitly adjust our swing path to make the ball work from right to left. Therefore, if we just aimed way to the left, expecting to hit the ball straight, it would end up in the trees. The implicit learning is actually making the explicit strategy not work. Returning to this study, when the rotation was turned off, participants made large errors in the opposite direction, again showing that implicit learning was going on. So even though they were given a highly effective explicit strategy to achieve the task, and it initially worked perfectly, they couldn't sustain it, but instead learned the task implicitly. Interestingly, when the magnitude of implicit learning, measured by looking at the difference between the aim point and the actual movement, was compared for a group that had the cheat code and a group that did not, the time course of implicit learning was not significantly different. However, the group without the cheat code learned to perform the task better because there was no conflict between the explicit aiming strategy and implicit learning. In sum, this study shows that explicit strategy to correct movement errors cannot be sustained because your perceptual motor system is going to naturally recalibrate and learn implicitly whether you like it or not. The authors nicely summarized the findings. Quote, "We conclude that adaptation to visuomotor rotation is independent of explicit strategies, and that the motor system overrides an explicit strategy when a conflict is present. Sport coaches take note that, when it comes to motor learning, the brain has a mind of its own." End quote. The next study I want to look at is one published in 2011 by Benson and colleagues. In their paper, the authors asked a similar question: can explicit instruction enhance implicit recalibration, or does one override the other? They proposed that a factor that might influence this is the amount of rest. Specifically, they hypothesized that when more time is given between trials, participants might be better able to integrate their explicit strategy with the proceduralized knowledge developed through implicit learning. 54 participants were randomly assigned to one of two groups, an implicit learning group and an explicitly instructed group. Within these two groups, participants were further divided into subgroups that were given 1 or 7-second breaks between trials. The task again involved moving a joystick to move a cursor towards a target on a screen. Participants in the explicit group were shown a diagram of a clock face and told that their movement would be rotated by 30 degrees. They were then shown if they moved towards 12 on the clock, the cursor would go to 1 o'clock. and were told that they could compensate for this by aiming at 11 instead. So very similar to the cheat code from the first study I discussed. Within the experiment, there was also randomly placed catch trials in which the rotation was turned off, and participants could not see the movement of the cursor. These were indicated by text on the screen. Participants in the explicit group were told not to use the aiming correction strategy on these trials. Participants in the implicit group were given no instruction at all before the rotation trials. They were also told there would be catch trials, and for these they should attempt to hit the target in the same way as on the other trials. There were a total of 304 practice trials with rotation for both groups, after which there were a set of trials with no rotation to measure after effects. What was found? Again, like the first study I discussed, initially the explicit strategy worked effectively at reducing errors almost to zero. But it came at a cost. Participants in the explicit group were slower to react and had lower precision, as assessed by trial-to-trial variability in the movement direction, as compared to the implicit group. The authors proposed that the longer reaction times reflect the increased cognitive load required to use a conscious explicit strategy. Participants in the explicit group also showed significantly smaller after effects in the catch and post-training trials, suggesting that less recalibration in implicit learning was occurring. There was also evidence that some of the participants in the explicit group eventually abandoned using the explicit strategy in favor of using the more effective and less demanding implicit recalibration. Finally, there was no evidence of differences between the groups given 1 versus 7-second rest between trials, suggesting that this time does not influence how explicit and implicit learning interact. So in sum, this study shows that while adopting an explicit strategy for correcting movement errors can be advantageous in getting rid of the errors more quickly, it comes at a cost of being slower, more cognitively demanding, and less precise. And more importantly, it can, in some cases, attenuate recalibration and implicit learning. The last study I want to look at today is a really interesting one published this year in Nature by Miyamoto and colleagues. In this study, the authors used a more complex visuomotor rotation manipulation to examine the effects of both explicit and implicit learning. An important difference between this and the previous studies I've talked about so far is that participants were not given an explicit strategy cheat code. Instead, they were allowed to develop it on their own. It is possible that we may get more positive complementary interactions between the two types of learning if the explicit strategy is self-generated. In this study, 41 participants completed the classic visuomotor adaptation task in which they moved their hand to move a cursor on the screen towards a target. Before each movement, they were asked to position a marker at the aim point, which of course can be used to assess the degree to which they're using an explicit strategy. And again, implicit learning was defined as the difference between the aim point and the actual hand motion. Here's where things get a bit different and a bit more complicated. Instead of having a constant magnitude of rotation, like the 45 and 30 degree values used in the two previous studies I've talked about, the amount of rotation actually changed from trial to trial. It was determined using a sum of signs function. To understand this, let me give you a very simplified example. Imagine I started by adding a 10-degree rotation every 10th trial. So 10 degrees on trial 1, no rotation at all for the next 9 trials, 10 degrees on trial 10, and so on. To that, let's add a different frequency of rotation perturbation, every 5th trial. So now, if we add these two together, we would get 20 degrees of rotation on trial 1, because both add together, 10 degrees on trial 5, 20 on trial 10, and so on. If we keep adding frequencies, we're going to get a complex sequence of rotations that change over time. So the performer is not only going to need to learn to recalibrate to a rotation, but also learn the temporal patterning of when to change the calibration. What this allows the researchers to do is a frequency analysis. So break down the movements in terms of frequency. What we should see is evidence of learning in the form of changes in the aiming point for explicit learning and differences between the aiming and actual movement for implicit learning at the frequencies we perturb the rotation. So if we perturb by combining frequencies every 5, 10, 20, and 40 trials, we should see the direction of aiming and movement change at these frequencies. What we shouldn't see, if learning is effective, are changes at other frequencies, say 2, 4, and 6 trials, because there's no perturbation at these frequencies requiring correction of the movement. In the study, training involved a total of 768 trials, and there were 5 sign components to the perturbation of 48, 96, 192, 384, and 768 trials, corresponding to 16, 8, 4, 2, and 1 cycle. Each was 10 degrees in amplitude. Note, because these are sine waves, sometimes they combine to produce a positive amplitude, a clockwise rotation, while in other trials they would combine to produce a negative rotation, a counterclockwise. As a result of this procedure, the values of rotation in the sequence range between minus 30 and plus 30 degrees, but changed very gradually, such that the biggest change from one trial to another was only 2.5 degrees. What was found? Overall, participants learned this task quite well. If you combine the explicit and implicit learning effects, the angle of movement follows very nicely the pattern of perturbation, with only about a 3 degrees overall error. As expected, the frequency analysis revealed that the combined responses were made at the perturbation frequencies and not at other frequencies. So unlike in previous studies I talked about today, when you look at the perturbation frequencies, explicit and implicit learning seem to be working together synergistically, combining to result in overall good performance. But here's where things get really interesting. As I said, the explicit strategy of adjusting the aim point seemed to combine with the implicit recalibration to produce the ideal amount of adjustment for the rotations in the experiment. However, on an individual level, there were significant differences in the relative contributions of these two types of learning. Some individuals used mostly explicit, while others used mostly implicit. Which was used also depended on the frequency of the perturbation, with explicit strategy learning used for higher frequencies that required more rapid changes, and implicit learning used for slower, lower frequency changes. When performance was analyzed at the non-perturbation frequencies, something else interesting was found. The two types of learning opposed each other and interacted antagonistically rather than synergistically. Why did the two go in opposition to each other at the non-perturbation frequencies? Because the antagonistic interaction, which makes the combined input sum to 0, improves overall performance. We don't want any movement correction at these frequencies because there's no rotation there. Next, the authors asked, at the non-perturbation frequencies, which type of learning was responsible for doing this cancellation? To do this, they fit the data with a structural equation model with different interactions between implicit and explicit learning. The best fit for the data was from a model in which implicit recalibration compensated for errors produced by the explicit strategy. This was also supported by a temporal analysis showing that the implicit learning lagged behind explicit learning, so that the former corrects for errors produced by the latter. Recall that in this study there were also large individual differences in the relative amounts of implicit and explicit learning used. Well, this had a direct consequence on performance at the non-perturbation frequencies. To quote the authors, given that adaptation at perturbation-free frequencies is largely idiosyncratic across individuals, which is in line with it being primarily driven by random sensorimotor noise, the finding that implicit learning actively responds to strategies at this frequency indicates that it acts to compensate for noise originating from strategy adaptation. If noisy strategy adaptation was the primary driver of perturbation-free adaptive responses, one would expect individuals with higher strategy levels, who should display greater levels of strategy noise, to exhibit systematically worse task performance than low strategy individuals. This is because effectively compensating for strategy noise would be more challenging in higher strategy individuals. An analysis of the individual differences in task performance revealed that this is indeed the case. We found a positive relationship between overall strategy and task error across participants, which indicates that participants with larger levels of overall strategy also exhibit larger overall errors. Together, these results indicate that high strategy participants exhibit systematically larger errors, which is in line with the idea that implicit learning acts to compensate for noisy, low-fidelity strategy adaptation. End quote. So in other words, due to their noisy and imprecise nature, explicit strategies introduce an error in the form of correction to movement at the non-perturbation frequencies where it's not needed. For performers that use less explicit learning, this is okay because these errors can be compensated for by less noisy, higher fidelity implicit learning. But for mostly explicit learners, the compensation is not complete, resulting in worse overall task performance. In sum, this study shows that an important function of implicit learning seems to be taking a compensatory role in cleaning up the inappropriate responses arising from a low-fidelity, noisy explicit strategy. It also again suggests that adopting an explicit correction could have a negative effect on implicit learning and overall performance. Quote, promoting explicit strategies may interfere with the development of implicit motor learning. In the current study, we found that implicit learning is attenuated by explicit strategy on an individual participant level, with a strong negative interindividual correlation between the amounts of implicit learning and strategic learning at perturbation-driven frequencies, which means that individuals with higher perturbation-driven implicit learning display systematically lower levels of strategic learning and vice versa. These behavioral findings are consistent with other work showing that the neural systems underlying explicit and implicit processes may competitively interact. And quote, this can make the overuse of strategy detrimental during the late stages of learning, where overall performance is appropriately centered and achieving precision is the dominant factor, because the use of a low-fidelity strategy reduces precision, end quote. So what should we make of all this, and what are the implications for coaching? Well, from the studies I reviewed today, it's clear that adopting a strong explicit strategy to correct movement errors has a negative effect on implicit learning. Explicit strategies are inherently slower, more cognitively demanding, more noisy, and lower fidelity, and cannot be effectively sustained. Implicit recalibration seems to happen whether we like it or not, and while it can compensate for some of the errors produced by the explicit strategy, the compensation is not sufficient when there's a heavy reliance on explicit learning, which results in overall poor performance. This occurs both when performers are instructed about the correction strategy, i.e. given the cheat code, and when they figure it out on their own. While we have the usual caveats here that these are simple degrees of freedom lab tasks, to me it again provides evidence that we shouldn't be mixing and matching theoretical approaches. If as a coach you believe that implicit learning plays a significant role in skill acquisition, then the work I've talked about today suggests that it will be counterproductive to try to also promote explicit learning at the same time by giving instructions about movement or technique, and/or by encouraging an athlete to reflect on their correction strategies. In the end, this will just interfere with the implicit recalibration of the information-movement relationship. Okay, that's it for today's episode. Remember, you can contact me at robgray@asu.edu or follow me on Twitter at ShakyWeights. To find out more about the podcast, please check out perceptionaction.com. Finally, to support the podcast and receive bonus materials, including written transcripts, please head over to patreon.com/perceptionaction. This is Rob Gray from ASU. Cheers for now, and keep 'em coupled.